Well, good morning. This is the lecture 6 on delivered on January 24th. Remember, there's a test coming up on Thursday, 26, and we're going to have it in the tutorial room. You are responsible for the content of this lecture. As a matter of fact, Thursday morning in the regular lecture hour, I'm going to do some practice problem and think about it as a review by doing some sample problems. Now, later that day, later on Thursday, January 26th at 3 p.m., you will have your test number one, and the duration of that is going to be 70 minutes. So 15 minutes of your tutorial time plus the 10-minute recess that we have between classes. And I managed to get 10 minutes off the next class. So that'll give you 70 minutes altogether. There will be 20 multiple choice short answer questions and a problem to do, regular problem to do with hand calculations. Okay, uh, let's move on. So the agenda for today is talking about the estimating the damping ratio using this thing called logarithmic decrement. And then I will do, so far we have done only viscous damping, where basically the force, damping force was proportional to the velocity, or F equal to Cx dot. Today we're going to do Coulomb damping, which has a different requirement. I will show you also how to experimentally measure mass moment of inertia of three-dimensional objects. Because remember, when we do vibrations, when you're dealing with rotational motion, you need J, or mass moment of inertia, uh, about certain axis or about certain point. And then I talk briefly about the concept of stability versus other or instability. Okay, so let's move on. Now, logarithmic decrement is a technique for estimating system parameters, in this case, the damping ratio, for example. So let me remind you that in order to do simulation, you need to know the parameters of your system. For example, the stiffness of your structure. Let's say we're dealing with a mass spring damper system. You need to know the stiffness of the spring. Of course, obviously, you have to know the mass, and that is the easiest one probably to measure. But the C is rather difficult. C, which is related to the damping ratio, is the most difficult to measure. So let's say that you actually took some measurements. Pretend that we are dealing with a single degree of freedom system. You took some measurements, and for example, displacement of a particular point, or your or your mass, uh, actually as a function of time. Uh, I want to remind you that when we do single degree of freedom system, the solution to our displacement, or your degree of freedom, it can be displacement, it can be rotation, is given in terms of this expanded form, this rather unique form that some textbook, including ours, is using. So this is the psi is the damping ratio, omega in natural frequency, and omega d is the da, da, damped natural frequency. Phi is the phase angle, and A is the amplitude of vibration. Of course, notice that the amplitude diminishes as the function as time goes on, because it's multiplied by e to the minus something. And as t gets bigger, this e to the minus gets smaller, and therefore the amplitude, which is this combination, the two of them together, is going to get smaller and smaller. So in a sense, for a viscous, for the case of viscous damping that we're looking at, the solution X, if you plotted it, it looks like that. And in fact, these dashed curves are called the envelope of the vibration, and some people also call it the decay rate curve. Okay. So let me remind you that the distance between two peaks is actually the period associated with this damped natural frequency, okay? So logarithmic diagram, let's concentrate only on these two peaks. Although what we do is irrelevant which two peaks that you take. In fact, can take many, many peaks. We'll come to that later on. Let's concentrate on x1 and x2. So if you form the ratio of x1 to x2 at these two times, and take natural log of it, we get this, and that is called delta, represented by delta, and it's called the logarithmic decrement, okay? It's called logarithmic because you're taking logarithm, and decrement because something is decaying, basically. Now, if I take out of the solution that you see up here, out of the solution, if I take and stick it in this expression, x of t1, so calculate this thing at x of t1, calculate this thing at t1, calculate at t2, this is what you're going to get. All I did, I took this expression, put it in the numerator and denominator, and put the time for the top as t1, see that? And the time at the bottom, t2. Now, let me remind you that T2 that appears here, T2 that appears here, uh, is in fact T1 plus the period, damped period. So what I have done, I've taken this T2 from that expression, it's appearing there in the exponential and in the sign, and replaced it with T1 plus the period, T1 plus period. Let's move on. I have expanded it. Another one multiplied that omega d by t1 plus t. I've expanded that. You see that? So now it's omega d t1 plus omega d t, big T. And I want to remind you that this t is actually period of the damped oscillation. Therefore, the relationship between omega d and t is this. So t is equal to 2 pi over damped frequency. Or the product of these two is actually 2 pi. So if I remove this, if I remove this fellow over here, if I remove it and make it 2 pi, notice that I have sine of something plus 2 pi, and we know from trigonometry that sine of something plus 2 pi, you can ignore 2 pi, and it's going to be the sine of that entity, which cancels the thing on the bottom, the top. So this expression sine on the top cancels this expression sine in the bottom, because all we have done is add 2 pi to this argument here. Now, the other thing is that notice that in the first two terms, the a's cancel and the term involving t1 cancel. The only thing that stays there is big T. So this cancels that, except that e to the minus psi omega and t is still there. So this is what we get. So this is because of all the cancellation. The signs cancel, the exponential, the terms that involve t1 cancel for the exponential, and the only thing that remains is the a's cancel is e to the minus psi omega n t. All right. Now we know from basic algebra that this is 1 over e to the minus properties of logarithm. All that you do is this psi omega n t ends up in the front, and you get ln of e, which is 1. So all I'm saying is, please look at your high school algebra, or high school algebra, and this is what you get. The psi omega and t moves in the front, and ln of e is 1, so this is what we get. Now, this t, we just had it up here, is 2 pi omega d. And omega d, in terms of the undamped natural frequency, was this expression, omega d equal to this, okay? So if you look at it, uh, t times omega n, see that I have here? Look at this expression on the top, this expression. T times omega n is simply 2 pi over square root of 1 minus psi squared. So all I did, I took this thing and rewrote it as t omega n, multiplying these two out, multiplying both sides by omega n, you get this. So that t omega n that appears in the expression of the logarithmic decrement, we can take this and replace it with 2 pi over square root of 1 minus psi squared. So I wrote it here for your convenience. So I did that replacement, and out of this, we can solve for zeta there. So zeta, in terms of the logarithmic decrement, is given by this, where the logarithmic decrement is nothing but x1 over x2. The moral of the story is this. Let me get the curve here for you. Look at what happened. Just bear with me for a second. You have x1 and you have x2, so you have delta, logarithmic decrement you have. If you have the logarithmic decrement, then you go here and plug it in, and you're going to get an estimate of the damping ratio. Now, notice that if you look at this expression, if the damping is very light, if the damping is very light, this denominator, the logarithmic decrement is going to be very small. You see, light damping means that x1 and x2 are very close to each other. So this is very small because we're taking log of something that's very close to 1, right? And this denominator can be, the delta square in the radical can be dropped in favor of 2 pi squared. Okay? And if you look at it, you get zeta equal to, the damping ratio is equal to delta, logarithmic decrement, that you can read it off a graph divided by 2 pi. This is for light damping. Otherwise, you have to use this expression over there. Now, I used x1 and x2, but this thing can be done for any two peaks. Okay, it makes no difference. So I used it only for x1 and x2, but this would have been x2 and x3. It could have been x5 and x6, etc. Uh, and the other thing is that I use this. I use the value of x displacement. This whole business of finding logarithmic decrement could have been used for velocity, because velocity is sinusoidal, and that decaying could have been for acceleration, etc., etc. But Inman uses displacement. Now, uh, instead of taking two consecutive peaks, let me take x1 and all the way to xn plus 1. So let me consider all of these. So instead of relying on x1 and x2 to come up with delta, I can use x1 and all of these things, in fact, to come up with the estimate of delta, the logarithmic decrement. So let's say here's the situation. So if I call, since I'm using x1 and xn plus 1, I'm going to be using x1 and xn plus 1. You see that everything in the middle is going to pop up somehow. So logarithmic decrement, instead of being between x1 and x2, is between x1 and xn plus 1. So that's why I call this thing delta sub n. Now, if you take x1 over xn plus 1 and use this trick, x1 over x2, x2 over x3, all the way, notice that this is the same as x1 over xn plus 1. Now, property of log is that you can sum up the logs. Log of product is the sum of the logs. And each one of these is delta. This is delta, this is delta, this is delta, the way we did it in the previous two slides. So in fact, n delta. So this delta n, if you use x1 and xn plus 1, is going to be n times the logarithmic decrement. And if you're going to replace delta from the previous page, that's what you're going to get. So if you know how many of these peaks are you taking, n of them, and you measure between x1 and xn plus 1, find the logarithm or natural log of the ratio of them, then you have to solve it out of this equation. Solve for zeta. The previous slide was when we took only one reading. So this was delta, n was 1, and you got exactly what we had a minute ago. All right, another something that's obvious from this expression that I have here is the logarithmic decrement is 1 over n ln of, if you don't take consecutive peaks, You take between 1 and n plus 1, so you find the log of this ratio, and then multiple ln of that, not log of it, ln of it, and then multiply it by 1 over n if you're taking n segments. Now, there is something that's very useful, and that is estimating psi based on the number of cycles that the amplitude reduces by 50%. Now, I'm not suggesting to memorize. This is just something very, very handy. For example, if you took the pendulum and you brought it to a position and let it go. Let's say that hypothetically, this angle that you actually raised the pendulum by, hypothetically, let's say 10 degrees. So let it go. It start going back and forth and back and forth, and this angle, which initially was 10 degrees, is going to get smaller and smaller and smaller because of damping. At some point, it the 10 degrees become 5 degrees. That's what I mean by number of cycles to reach 50% amplitude. So if you counted these vibrations, these back and forth vibrations, these cycles, until the angle was halved, the original angle was halved, that is what's going to go in here. And you get the damping ratio based on that. And or in the case of a cart, for example, move the cart and to some position. Let's say you move it by I don't know, 5 centimeters, okay, and let it go. Now this is going to go back and forth, back and forth. Eventually, that 5 centimeter distance to the equilibrium position becomes 2.5. If you counted the number of times that this thing went back and forth, that would be your n 50%, and you plug it in that expression, you're going to get an estimate of the you're going to get an estimate of uh, the damping ratio. Okay, all right, let's move on. Let's do some examples. Suppose that we have a mass spring damper system here, and the mass is 2 kilogram, and on the right hand side we recorded the data, the displacement of the mass as we moved it to the right and let it go. For example, it traced this curve, this position of the mass, which I actually gave you this curve. Okay, that doesn't surprise you because if you assume that we have a viscous damper, the envelope is a curve like that. Now, uh, first of all, the mass is 2 kilogram, and you took this spring out and measured the stiffness of it, and you know how to do that. You apply a weight, you hang a weight to it to see how much it stretches, and the force, the weight of that thing that you attach to it divided by displacement is going to give you the stiffness of it. Okay, so suppose that this stiffness, either we knew it or we did the measurement, came out to be 1500 Newton per minute. What you want to do is based on this curve that was generated by actually measuring X, once we let it move, we want to estimate the damping ratio. So K is 1500. Now we're going to use the first two peaks. Let's say that the first one had the amplitude of 9, the next one had amplitude of 1. So logarithmic decrement is logarithm of x1 over x2, which is this number. Okay. Now that we have this, we can solve for damping ratio. You plug it in this expression, just plugging the numbers, 2.1972, and down here you square it, use your calculator, you're going to get damping ratio is 0.33. Now, if you want to know the value of the damping itself, the C value, you know the damping ratio, and damping ratio is just C over C critical. If you calculate your C critical, you can get your C. So let's go ahead and see how C critical can be calculated. This is one way of doing it, 2 square root of mk. You put your mass, you get your K, and you work it out. The other way is this expression is equivalent to 2 mass omega n. So if you calculated omega n first, you can also use 2m omega n and get the critical value. And the definition of damping ratio, which is C over C critical, simply tells you that C is equal to that. And there is your damping estimate, estimate of the damping coefficient C. Okay, so now we're going to move on from viscous damping to something called Coulomb damping. If you have this is very common, by the way, due to joint friction or surface friction. Okay, sometimes it's called dry friction also. Okay, so the issue with the Coulomb damping is that it's great, but immediately the equation that you're dealing, remember the mother of all equation, mx double dot plus cx dot plus kx equal to 0, that equation becomes nonlinear. So we already know how to find the first one because in differential equations course, we spend maybe a month on it. And here I did a review. All the stuff that we have done is basically the solution of the equation. But now if you use Coulomb damping, the equation becomes nonlinear. So let's first of all see what is it, how does it come out to be nonlinear, and what is the equation going to look like. So let's go ahead. If you take a mass, this is the block that is attached to a spring. See that there's a spring force here on the left hand side. Let's say we move this thing to the right. Here, we took the spring initially was sitting there. We moved it to the right. Okay. Now, if the block is moving by itself to the right, the friction between the block and the surface opposes that motion. So if this block is accelerating, moving to the right, basically, or accelerating to the right, the friction force is pointing to the left. On the other hand, if the block is moving to the left, the friction force is opposing it to the right. In both cases, notice that in both cases, the spring force is pointing in the same direction. So the equation of motion, so right there, this is what I said. Okay. Now, uh, the equation of motion becomes this: mx double dot plus kx equal to this number. This is the force of friction. It is just the normal reaction force times the kinetic coefficient of friction. This mu. This is the friction force from first year of statics. You know that it is mu, coefficient of kinetic friction, times n, normal reaction force. And incidentally, n is mg here. Okay, but this sign changes depending on whether the thing goes to the right or it's moving to the left. Okay, still to the right of the equilibrium point, but if the block moves to the right, it's this equation. If the block moves to the left, it's this equation. Okay. Now, the coefficient of kinetic friction for certain situation is taken from a table in the book. So, if, for example, metal on metal, uh, lubricated 0.07, wood on wood, it's harder to move. There's more friction, 0.2. Uh, steel on steel unlubricated, it's even worse than wood, and rubber on steel is terrible. Okay, kind of sticks to it. Okay. Now, those two equations that I had in the previous case, each one of them we can easily solve because those are things that you did in your differential equations course. I don't expect you to solve that, but I'm giving you the solution. It's so simple. Okay. So here's the situation. So if you look at a cycle, a cycle of this process, in the first cycle, the equation looks like this, solution looks like that. And in the second cycle, the solution looks like this. In fact, I'll show you this thing graphically, but at least so that you know where it's coming from. It's coming from here. Now, this assumes that the block is displaced to a position and released from rest. Okay. So here's the situation. Some observation. Remember, when we did the viscous damping, the solution looked like that, but the envelope was not a straight line. In the case of Coulomb damping, the envelope is actually a straight line. So if you took all these peaks, you connect it together, pretty much you get a straight line. So the amplitude decays linearly rather than exponentially in the viscous damping case. If you see a curve here, this is viscous damping, if you see a curve. But if you see a straight line, it's better represented by Coulomb damping. Now, at some point, after going back and forth, this block will actually stop, literally stop. And that stops when the force of the spring is actually less than the force of the friction. And the force of the friction, uh, this is the, the force of friction is mu k, mu n, the force of friction. Force of the spring is, k times wherever it's located. The moral of the story is that for viscous damping, the block never stops. It gets closer and closer to the equilibrium position in theory, but it never stops. Real life is a different situation. But for Coulomb damping, whenever it, it reaches a position where the force of friction, okay, force of friction, which is mu n, is uh, bigger than kx basically, K being the stiffness of the spring times X, the position where the block is sitting, it's going to stop. Now, the other thing is that if you look at the frequency of oscillation in Coulomb damping, that's omega n, not omega d. In the viscous damping case, the frequency of oscillations with a viscous damper was omega d. It's a little bit smaller than omega n. Not in the case of Coulomb damping. As a matter of fact, when you go and look at the solution, let me back up for a second. Notice that it's cosine of omega nt, not omega dt. There is no such a thing as omega d. Okay, so let's go ahead. Now, the real world situation is neither viscous nor Coulomb damping. Uh, my example is this: you take some object, take it to the outer space, and stretch it, and let it vibrate back and forth. Eventually, it will stop, guaranteed. This is not happening because there are any joints. Because all you did, you took a rod and just stretched it and let it vibrate. Okay, there is no joints here, and there is no air resistance. There is no damper there, but it happens because the atoms slide on top of each other inside of that material, and that acts as a damper. Okay, so that is called structural damping or material damping that we will discuss later in the course. So let's summarize what we have learned in the case of Coulomb damping. First of all, the frequency of oscillation is omega n, not omega d. There is no such thing as omega d. Slope of this line, the slope of this line, see that? This is a straight line. The slope of the envelope line is right here, okay? So you have the coefficient of friction in there, you have the mg basically, n is a normal reaction force, mg, omega n is square root of k over m, and k is sitting there. And there are other ways of writing this thing if you use some of those relationships, but I'll leave it like this. In every cycle, this is one cycle of oscillation, the amplitude drops by that much. So if it was x naught initially, we moved it location x naught, after the first cycle is going to be x naught minus 4 of these. Every half a cycle, it obviously drops by half of that. One cycle, the amplitude drops by this much. Next cycle, drops by another this much, another 4 mu n over k. Now, the oscillation stops when force of the spring, which is k times x, is less than friction force. Okay, it's written a different way. So, for example, it says if the position is less than this, it's going to stop. Another way of saying it is force of the spring less than the force of friction. Okay, and if we look at n cycles, so you can write the amplitude after n cycles simply initial amplitude minus n times of these drops. And again, once again, it stops if mu n is less than k. Okay, this is saying the same thing. These are saying the same thing. The other way of looking at this formula that I wrote down is that if you look at the right hand side inequality and you solve for n, it says after that many oscillation, that many cycles, full cycles, the if you calculate the right hand side, find out, for example, I don't know, 7, for example, it says in 7 cycles the oscillations stop. So these are saying the same thing. Let's do an example. So we have a mass oscillating on a surface, and the data that we get, for example, based on the amplitude of oscillation, in other words, the distance of the mass, initially when you moved it out, you got some distance, let it go back and forth and measure the maximum distance to the equilibrium position. Those are called amplitude. Okay, it follows that. Okay, and it says that initial position is 30 millimeter right here, for example. If we start with this. Okay, and the rest position is 3.5 millimeter from the zero rest position. So basically, it says initially, it would have been better if I took this 30 and wrote it here, and this 3.5 wrote it there. Okay, but anyway, we didn't do that. So it says initial position is measured to be 30 millimeter from rest position. Because you might say that, hey, wait a minute, that's not the initial position. The initial position is here. That's why I said it's better if I took this 30 and put it there. And the final position is measured 3.5 from its the zero rest position after 4 cycles. Okay, so four cycles of oscillation in 1 second. So out of this 4 cycles in 1 second, it gives us the period of oscillation. Look, this is a horrible drawing because in this 1 second, there's 4 cycles. This is a terrible drawing, but please clean it up yourself. There should be 4 of these, okay? So first of all, we don't need this graph, although it may help, but this graph is not consistent with what it says here. It says 4 oscillations, 4 cycles. This is not 4 cycles. Between these two, I have only uh, 1 cycle. So frequency, this was 4 cycles converted to radians per second. Actually, I have to eat my words here. So it says we noticed that 4 cycles in 1 second. So the frequency, so this is 4 hertz, right? Oh no, that's okay. 4 hertz, 4 hertz times 2 pi. That's going to be 25.13 radians per second. There's nothing to swallow here. I said I have to swallow my words now. That's okay. It says 4 cycles in 1 second, so that's 4 hertz. And in radians per second, it's going to be multiplied by 2 pi. It's going to be 25.13. Now, the slope of this line, uh, the slope of this line is uh, all you have to do is, first of all, you can take the 3.5 minus 30, 3.5 minus 30 divided by that time, which is 1 second. So minus 30 plus 3.5 over 1, that's going to be the slope of this line. And we write down the expression that I gave you for the slope of this line. Go to the, the 3-4 slides back. I wrote the expression for the slope of that line. It was this. So the different ways of writing these things, as I said, there are different ways of writing these things. You can, for example, you can write uh, K as M omega n squared, okay? And, you can do a cleanup there, whatever is convenient for you. I mean, you don't have to do what I'm doing. We know the slope of the line. It's this or that. This is cleaner than this, okay? So out of this equation, what we do not know is mu. We want to find the coefficient of friction. We know G, we know omega n, we just did it up here. You'll solve for mu, and this is what you're going to get. Okay? We were given the frequency of the oscillation. Omega n is given to us. We were given the slope of this line based on the data provided. The only thing that we don't know in this equation, if you jump from here to here, these are okay, but I simplified these, is just solve for mu, coefficient of friction. Here's another problem. We have a 2 kilogram mass connected to a spring of the stiffness. So we have mass and we have K, and we are doing Coulomb, as soon as I say sliding friction, dry friction, we talk about Coulomb's law. And this is the friction force. Now, all that means is that 3 newtons times mu. This 3 is actually capital N. This says 3 N, Newton, but that is not what I'm talking about. This 3 is big N, which is your mg, and then you have to multiply it by mu. So this 3 is mu times N. So immediately, if you want, you can go ahead and calculate mu out of this, okay? Immediately. But anyway, let's move on. What is the kinetic coefficient of friction? So mu, okay? And after how many cycles does the amplitude decay by 20 centimeters? So here's the situation. Force of friction is equal to mu times big N, normal reaction force. So it's going to be 3. We are told that the numerator is 3. The normal reaction force is mg, right? Big N is mg, okay? It's unfortunate because this N is Newton, and the big N that I'm talking about, normal reaction force, is mg. So you plug it in, you're going to get your coefficient of friction, kinetic friction. Okay? I was saying that 3 is mu times big N, normal reaction force, and 3 mg. Okay, so we had this formula which we are told that uh, the amplitude has decreased by 20, so this means that xn minus x naught. We don't know in how many cycles, but we know that xn minus x naught is 20. So if you rewrote this xn minus x naught, we are told that this number is 20 centimeter. We know mu, we know big N, we know K. We can find little n, which is your number of cycles. So this is minus 0.2, 20 centimeters, 0.2 meters, okay? 4 times mu times N, okay? Force of friction, 3 right there, divided by K stiffness of the spring. And out of that, you're going to get N is approximately 17 cycles. So this happens, the 20 centimeter reduction in amplitude happens in 20 cycles. Let's do another problem. So we have a 15 kilogram mass attached to a spring of stiffness. So we have the M, we have the K, and we have the coefficient of static friction, kinematic friction. So basically, we are deemed Coulomb law because friction is given here to us. Okay, find the number of cycles for 50% reduction of amplitude. Okay. Uh, Assume that the block is initially positioned. This shouldn't be B. Initially positioned at 5 centimeter from the equilibrium position. So all that says is that, okay, we are going from 5 centimeter amplitude to 2.5 centimeter amplitude. In how many, in how many cycles? Okay, so you look at this expression, xn minus x naught, we actually have it. Okay, so xn 0.25, which is half of this original one, okay? And everything else I have here. So this is the coefficient of friction. N is 5 kilogram times 9.81, right? This is the weight. And big N, The normal reaction force is mg. M is 5, g is 9.81, divided by k that's given up here. Notice that this is a 50% reduction from 5 centimeter went to 2.5 centimeter. And solve for n, you get approximately six cycles. But if I use 6.25, that's okay. Just leave it the way it is. And it says find the time taken for this to take place. So what we really need is the period of each cycle, and there's 6 of them. So we multiply 6.25 of them, multiply by that period, we're going to get the time taken for this reduction to take place. So in order to find the period, I need to calculate omega n, the frequency, and period is just 2 pi over omega n, which is 0.634. So each cycle takes that much. There is 6.25 cycles. You multiply them out, you get 3 point, almost 4 seconds, 3.96 seconds. So it takes 3.96 seconds for that block that was 5 centimeter away from the equilibrium position to go to the 2.5 centimeter from the equilibrium position. That's what this is saying. All right, so now we're going to shift gears. We're going to go to something called measuring mass moment of inertia. Obviously, moment of inertia is important. So I'm going to show you a way of measuring it experimentally in the lab. Use a pendulum. It's called tri-filler suspension device. So we assume that this object that we are trying to find is mass moment of inertia about a certain axis. Whenever you're talking about mass moment of inertia, you have to say about what, okay? So what we're doing here is we are finding it about a certain axis going to the center of mass, okay? So here's a situation. Suppose we create a pendulum, not pendulum, what is it called? Suspension device like this. I mean, in reality, it may look complicated like that, but let's think about it as a tray here with a disc. Let's call it a disc, okay? And we take this object that we're trying to find its mass moment of inertia about an axis going to the center of it, vertical axis. So we place it there, and we want to find the mass moment of inertia about this vertical axis passing through the center of the disk, which is immediately above it is the mass center of this three-dimensional object. Okay. All right. So you place this object. So that its mass center sits exactly at the center of this suspension disk. These are suspended by some ropes, wires. Okay, so this is a simplistic view of an actual, suspension that you do in real life, but it's a simplified version of it. So here's the situation. So there is my block. Its mass center sits exactly above the center of this disk. So what we're going to do, we're going to take this disk and rotate it a little bit, small angle, say theta angle, and then let it go. When you let it go, this disk begins to, and these are the wires, by the way, these are the cables. You can see that when you rotate it, they become, instead of being vertical, they become at a slanted angle. This thing begins to oscillate back and forth in a torsional mode. So let's look at what we need in order to do this. L is the length of the rope. So L is the length of the rope. R naught is the disk, the radius of the disk. There is a disk. I naught is mass moment of inertia of the disk about the vertical axis. We know that it's usually, it is 1/2 mr squared. You know that. I naught is the mass moment of inertia of the disk about its center. That's what this thing is. M naught is mass of the disk. M is the mass of the object that we are trying to find its mass moment of inertia. G is the gravity constant. T is the period of this oscillation, because you're going to be measuring the period of this back and forth oscillation as you twist this thing a little bit and let it go back and forth. And I is what you want to find. I is the mass moment of inertia of that three-dimensional object about its mass center in the vertical direction. We want to find I. So I want to show you that that I that you're trying to get by this experiment is simply this expression. And in this expression, we know everything. T is the period of oscillation. We know everything else, and that's going to give you I, the mass moment of inertia of that object about an axis through its mass center in the vertical direction. And how do we get this? Where does this thing come from? So let's go ahead and look at this thing one more time. I've drawn it here for your convenience. If you look at this setup, this originally vertical cable, I'm looking at one of them, this vertical rope or wire, which is tilted a little bit. It's gone through an angle alpha, and of course the disk has rotated by the angle alpha. This angle alpha and that theta are not the same, they're related, because if you take alpha and multiply it by L, you get this arc, and if you take theta and multiply by R naught, you get this arc. So there we are. L times alpha is going to give you that length, and theta times R naught is going to give you the same length. So there is the equation. Now, look at this triangle. The length of this is L. The length of this, say, Pythagorean theorem, or the hypotenuse of this triangle is L. This angle is alpha. The force is the weight. If you take the mass, if you take the mass of the disk and the mass of a three-dimensional object and add them up and multiply it by g, you get the weight of this suspension tray and the mass in it, and it's divided equally between the three cables. So that's why I have this weight, the tension in that. Think about it. It's not quite the tension in the rope, but think about it as well, if it was not rotated, it would be the tension in this wire, okay? 1/3 of the sum. Now, what is causing this thing to go back and forth is actually a moment, and the moment is the component uh, well, it's this thing, right? It's the component. Uh, it's this component. That component, think about it, makes this thing rotate, okay? Make this thing torque. And if you look at this triangle, this angle is alpha, and this length we know is right here, and this is going to be the tangent, that thing times the tangent of alpha. So for small angle oscillation, we're talking about a tiny amount of rotation of this disk, okay? So if you look at this triangle, this length is given here, 1/3 of the weight of the assembly, and this angle is very small, so that is equal to this length times the tangent of that. But for small angle, tangent of alpha and alpha are the same, so there we go. This force, which is actually has a moment arm of R naught about the center of the disk, is responsible for the restoring force. This is the restoring force. This is the restoring force. So we write the usual sum of all the moment about the z-axis equal to I about the z-axis, which incidentally is I plus I naught, right? Because it's the I of the disk, and I naught that we're trying, I naught is for the disk, and I is what we're trying to calculate. So this is going to be I plus I naught times the angular acceleration. So I plus I naught times theta double dot is equal to the torque. The torque is going to be this force multiplied by the moment arm, okay? And there's three of them because there is three such forces acting on each side. Okay, moment arm, yeah. Okay. Now this alpha, we're going to get rid of it based on the expression that I have up here. Based on the expression that I have here, which is this, I'm going to get rid of alpha. You plug it in, no more alpha there. And I take everything to one side. These are all, this has a theta double dot in it and a theta in it. So take it all to the right hand side or left hand side, and you get this. This is the mother of all equations. Something times second derivative with respect to time. No damping here. We are assuming there's no damping, and something times the angle. This is like M effective X double dot plus K effective X, except that I don't have X, I have theta. Okay. So the natural frequency of this oscillation of this pendulum is there. If I square it, you get this. And remember, the natural frequency and the period are related through this very simple expression. You plug it in, so you're going to get K effective over M effective equal to 4 pi squared over T squared. Why I did this thing is because I want to uh, uh, find what these things are. I know this. This I can measure because T I can measure, right? K effective is actually this horrible expression in the front of theta. And M effective is that guy, I plus I naught. So if I plug these things in, K effective is this coefficient, M effective is I plus I naught, right there, and you clean it up, you solve this thing for I, the only unknown in this expression, cross multiply, clean up, you're going to get this. So everything on the right-hand side, including the period of oscillation, you know, and you're going to get the mass moment of inertia about the vertical axis. Now, the last item that I want to discuss today is the concept of stability. If you look at this equation that we have dealt with it many, many times, remember, I write x here, but this x can be actually an angle, doesn't have to be a displacement, okay? That's what we refer to as mother of all equations. Now, first of all, every problem that we have done, mk, and c, these were positive numbers, okay? Mk and c are positive numbers, there's no doubt about it. And the scenarios that we come across is either, this is either undamped, which means, by the way, C is 0, overdamped, where xi damping friction is bigger than 1, underdamped, where xi is less than 1, or critically damped. Okay, so as long as mk and c are positive, these are the only things that can happen. Now, and we know how the solution looks like. For example, in the case of this is viscous damping, you can have a oscillating, decaying amplitude, or overdamped and critically damped, which are not oscillating like that. And if there is no damping, C equal to 0, obviously it's a sinusoidal curve. Now, what if in this mother of all equations, some coefficients are negative? Now remember that there are problems that we do where the coefficient in front of theta double dot or x double dot is not just k, it's some kind of a k effective or m effective. And the thing that's multiplied by x dot or theta dot is not c, it's some kind of a number, c effective, okay? And the thing that's multiplied by theta or x is k effective. So what if one of those effective stuff is negative? In that case, if the k is negative, for example, one of them is negative, you will have unbounded oscillation. Okay, and that's what we call unstable. And well, if it looks like that, it's called divergent instability. If it's like this, called flutter instability. Wing flutter is something common cause of crashes, and therefore you see, for example, displacement grows, etc. Now, I want to show you an example. We have already seen an example of this inverted pendulum. We saw this thing in the class, I think probably last week. Yeah, I think it was last week. And the drawing looked different, but it's exactly the same problem that I showed for you, except that those two springs, I just drew it on one side. It doesn't matter, these two springs are actually parallel, and therefore all you need to do is to draw one of them, and basically it's a pendulum with a bulb on the top attached to a spring. We did this problem. Okay? We're going to do it again. So if you look at the free body diagram here, we're assuming that this rod is massless. If you look at the free body diagram, there is the weight at an orientation theta. So this rod actually tilted. It tilted by the amount theta, so I've drawn it here. There is the weight of the object, there is the force of the spring, and there is the reaction force. Now, reaction force, it doesn't bother me because we're going to take moments about the pivot point, okay? So it doesn't matter what FP is. You take the moment of FP about that pivot point, you're going to get 0. And where does this thing come from? If you look at it, for example, uh, if you look at the deflection of the spring, okay, so first of all, the force of the spring, uh, well, force of the spring comes from the stiffness, and there's two of them, two springs here, that's why I have a 2 here. The stiffness is K, there's 2 of them, 2 springs. The stiffness of each is K, and then L over 2 sine of theta is actually the amount of stretching or compression. Okay, notice that it's actually L over 2 because that's a midpoint location, The inverted pendulum that I did for you in class, I might have called this thing A, okay? Might have called this thing A. But anyway, so you have the stretching or compression of the spring is uh, L over 2 times sine, but for small angle, sine of theta is the same as theta, so I'm going to replace this thing with theta. Taking moment about the pivot point, there we are. So this mass has a mass moment of inertia about the pivot point, which is just m times length squared, right there, theta double dot, okay? And what is that? This is the weight. Take the weight here, right there. This is the weight. This is the weight times the moment r. Moment arm is right here. Moment r about that pivot point is right there. So it's actually L sine of theta. Later on, we're going to assume sine of theta is close to theta. And what else do we have here? Oh, the compression of the spring. This is the compression of the spring. Okay. Uh, when this this thing tilts, the moment arm for it, is no longer L over 2. It is just L over 2 times the cosine of that angle. So this is the spring force. The moment arm, is L over 2 times the cosine of that angle, the projection along the vertical line. This is correct, okay? Except that it's not obvious where it's coming from. So let me say that again. Force of the spring times the moment arm. This is the moment arm. And that moment arm is this value, L over 2 times the cosine of that angle is theta. And for small angles, sine of theta is theta, cosine of theta is almost 1, sine of theta is theta, and we get this. And notice that this is the effective spring constant. This is the effective mass. This is the effective spring constant. For a certain combination K, L, M, and G, this may become negative, and that's where you have unstable solution. And think about it. I told you in class, if these are soft springs and you tilt this thing a little bit, if these are very soft, this will never oscillate. It'll just go to the right or go to the left. Okay? It just falls. Okay? So this is an equilibrium position, but depending on what MK, MKG, and L are, this may be negative. And if this is negative, that this structure is unstable. That's what instability is. Okay? And that takes care of the lecture for today. Uh, please keep in mind that this lecture, you are responsible for it on the test number 1.